So what is stoichiometry? Well, stoichiometry is looking at chemical reactions from a quantitative standpoint. You can make an analogy to a baker who might look at the amount of ingredients it takes to make a certain number of cookies or a certain number of cupcakes. A chemist might look at, well, how much of a particular reactant do they need to make a certain number of, or a certain amount of a product. So that's the question we're going to be able to answer through the use of the technique called stoichiometry. So what we'll do is we'll just get right into a couple of examples of this. Similar to a baker, a chemist always has to have a formula or an equation to, to base their calculations off of. So here we have a reaction between phosphorus and oxygen, and we're producing a compound that contains the two elements. So the first thing we need to do is have a balanced equation here. So just kind of remembering our balancing technique, we're going to put a 1 in front of the most complicated part. And then we're going to balance the phosphorus by putting a 1 over here, and balance the oxygen by putting a 5 in here. So now that we have our balanced equation, we're prepared to do some quantitative work with that equation. So the first one says, how many moles of the tetraphosphorus digoxide can be produced with 3 moles of oxygen and an excess of phosphorus? Given that we're going to see a lot of different wordings of problems, the first thing we're going to want to do is try to make all of them look similar or uniform. So I'm going to take the wording out of this by putting the amounts that we're given and the thing we're trying to solve for underneath the equation. So how many moles of the tetraphosphorus digoxide? So I know that that's what I'm trying to solve for, is how many moles of the product are formed. And I know that I start with 3 moles of oxygen, and I have an excess of the phosphorus. Okay. So we're going to use dimensional analysis in our stoichiometry here. So we're going to start with our 3 moles of the O2, put that over 1. And again, I know that I'm going to want to put moles of O2 on the bottom. And we're going to use the balanced equation then to convert from moles of O2 to moles of our product. Okay, and so if I look at the equation, I see that I've got, I'm going to use another color here. We've got a 5-to-1 ratio from the coefficients. So I know that for every 5 moles of O2, I will produce 1 mole of the phosphorus digoxide. And so then we get, do our calculation here, and whatever our number ends up being, we get 0.6 moles of the P4O10. So you can see that we just used the coefficients in the equation. Now you recall when we did the dimensional analysis problems with compounds, we would use mole ratios based on the subscripts in the formulas. So this is a similar kind of idea, only we're going from one substance to another using the balanced chemical equation. All right, the next one we have down here is the number of grams of oxygen that are required to react with 10 moles of phosphorus. So let me go back up to my formula, and I'm going to erase the stuff that I had there before. And let's use a different color here. So we want to know the number of grams of oxygen. So we want grams of oxygen are required to react with 10 moles of phosphorus. Okay. And in this situation, we aren't told anything about the phosphorus, tetraphosphorus digoxide, but we really don't need it. We're just trying to figure out how much oxygen we'd need to react with all the phosphorus. So again, I'm going to go to my dimensional analysis techniques. I've got, oops, not grams. I've got moles of phosphorus over 1. And I'm going to go moles of phosphorus Now, the balanced equation can get us from moles of phosphorus to moles of oxygen. And then it's just a matter of, again, knowing, where we are in this kind of, this mole map area, and realizing that, well, if I get to moles of oxygen, I can then very easily convert to grams of oxygen, because I know that a mole of oxygen molecules here would be 2 times 16, or 32 grams of oxygen. So, and then again from the balanced equation, what do we have? We have 1 mole of phosphorus to every 5 moles of oxygen. And then we just need to go through and figure out our numbers here. And we get 1.60 times 10 to the 3rd grams of oxygen that would be required to react with the 10 moles of phosphorus. So we really haven't used any new tools here yet. I mean, our mole-to-mole conversion that we did in each of these, right here and right here, were new in that it was the first time we used the balanced equation to create a conversion factor. But the gram-to-mole conversion that we used in the last one here for the oxygen, we're familiar with from before. So it's really just a matter of using the balanced equation to come up with that mole-to-mole ratio. Now, we are going to add a couple more conversion factors in here just to kind of expand our flexibility. So one of them is in working with gases. We'll do a whole unit on gases at some point in the year later on. But the one for right now is a conversion between the volume of gas and the number of moles of gas. So for gases, if you have a gas at STP, now STP stands for standard temperature and pressure. And standard temperature is 0 degrees Celsius, or 273 degrees Kelvin. And standard pressure is 1.0 atmospheres, or 760 millimeters mercury, or 101.3 kilopascals. And so those units will become more familiar with when we get to the unit on gases. But for right now, if you're told that you have a gas at STP, you know that 1 mole will have a volume of 22.4 liters. Again, that can be a conversion factor for you. The other one is in solutions, and we've dealt with this before in the lab. Molarity tells you the number of moles of solute per liter of solution. So again, this could get you from a volume of a solution to the number of moles of the solute that you have present. So again, that moles is our kind of our central hub, and so we kind of go back and forth from that. So a couple more problems here. So again, we start off with balancing the equation. We put a 1 in front of the most complicated part, which would probably be the ammonia here. We swing over and put a 1 in front of the nitrogen dioxide to balance the nitrogens. And then we've got to do either the hydrogen or oxygens. If I do the hydrogens, I swing over from the ammonia to the water, and I realize that I've got a problem with the odd even, so I'm going to have to double. So I'm going to put a 2 there, a 2 here, and then try again. Now I have 6 hydrogen on the left, so if I put a 3 here, that gives me 6 on the right. And now I can look at my oxygens. I have 4 oxygens in the NO2 part, and I have 3 in the water part, which gives me 7. And I run into another odd even problem, so I'm going to have to multiply again. But this should be, oops, excuse me, this should be it. So that gives me a 4 in front of the ammonia, a 4 in front of the NO2, and a 6 in front of the water. And so now I look again, and I have 8 oxygens in the NO2 and 6 in the H2O, which is 14. So I would then need 7 in front of the O2 to get 14 on the other side. So just to kind of refresh that we do need to have our balancing skills kind of at hand. All right, so the first question we have is how many grams of ammonia are required to produce 1.00 grams of water? So we're going to put 1.00 grams here, and we want to know the number of grams of ammonia that we would start with. Now, we kind of have to assume from the problem that we have an excess of the oxygen. So the wording of it indicates that we're not worried about the oxygen part of it. So we're going to start with our 1.00 grams of water. Put that over 1. And we're going to have to go grams of water to something. And so now we just got to figure out the way we're going to do this. Well, remember that the way we get from one thing in an equation to another is by using the coefficients in the mole ratio. So we can get from the water, right, we can get from the water to the ammonia from moles. So it makes sense then. The first thing we're going to do is go from grams of water to moles of water. So 1 mole of water, we look at the periodic table, is 18 grams. And now from moles of water, we can use the balanced equation to go to moles of ammonia. And again, let me just put this in green. So the balanced equation, there are 6 moles of water produced from every 4 moles of ammonia that react. And again, the question wants us to go to grams of ammonia, so then we would go moles of ammonia to grams of ammonia, and 1 mole would be 17 grams. And we should probably double check, just make sure we've, all of our units cancel out, and we end up with grams of ammonia. And so we can go through then and do our multiplication and division to figure out the number of grams of ammonia that would be required here. Okay. So next one down. So let's erase the values that we had here. And we'll work in blue this time. So how many grams of nitrogen dioxide, so we want to know grams of the nitrogen dioxide, are produced from 10.0 times 10 to the 25th molecules of oxygen? Okay, so this molecules have popped its head into things. All right, so let's start with that. So 10.0 times 10 to the 25th molecules of oxygen over 1. And so we know we're going to go molecules of oxygen to someplace from there. Now, here we actually have a choice because the equation tells us the ratio of moles. So if we go back up just a little bit here, we know that for every 4 moles of the NO2 that's produced, we had to use 7 moles of oxygen. But it also means that we have that same ratio in molecules. So we could go, one option would be go from molecules of oxygen to molecules of the NO2. So for every 7 molecules of oxygen, you produce 4 molecules of NO2. So this gets us to NO2. Now we just need to get to grams. So where do we go from molecules? Well, the only thing we can do to get to grams of NO2 is if we're in moles. So we need to get from molecules of NO2 to moles of NO2. And it's 1 mole is Avogadro's number, 6.02 times 10 to the 23rd molecules. And then once we're in moles, we can go to grams. So 1 mole of NO2 molecules would be 32, 42, 46 grams of NO2. The 16 for each oxygen and 14 for the nitrogen. And we can go through again, just double check, make sure all of our units cancel out. And yes, we're left with grams of NO2. And then we just need to pick up our calculator and do the punch in numbers in correctly. So you can see how these things kind of flow. They're oftentimes flowing through either moles or, in the case of this problem, molecules. And let's just do one more. Here's a volume one that involves using our gases at STP. And so what are we given here? So let's go back up. We want to know the volume of nitrogen dioxide for 24 grams of ammonia. So let's erase this. And volume of nitrogen dioxide. So we want to know the number of liters of nitrogen dioxide. And we've got 24 grams of ammonia. Okay. So again, we're going to want to go through moles to get from ammonia to NO2. So we're going to have to go from grams of ammonia to moles of ammonia to moles of nitrogen dioxide, and then we can use that conversion factor for gases that gets us from moles of nitrogen dioxide to liters of nitrogen dioxide. So I'll come back down here. Let me just remember the ratio there, and it's actually 4 moles of ammonia to 4 moles of NO2. Okay, so we have 24 grams of ammonia. And again, we need to get from one substance to another, we need to get to moles. So we go grams of NH3 to moles of NH3. 1 mole is 17 grams. And then 4 moles of the NH3 to 4 moles of the NO2. Again, using the balanced equation. So the 4s were the coefficients for each of those in the balanced equation. And then here's our new conversion factor. One of our new tools in our tool belt here is that if we have 1 mole of NO2 gas at STP, right now this only works if it's a gas STP, the volume is 22.4 liters. Now this is kind of a nice one for us. It seems like another hassle of things to remember, but in the scheme of things, we don't have to go to the periodic table to look for numbers and add things up. All we have to do is recognize that it's a gas at STP, and then the conversion factor is 22.4 liters to 1 mole. Doesn't matter what gas it is, we can use the same conversion factor. Double check, make sure our conversions all cancel out, our units all cancel out, and our answer would then be in liters of the NO2 when we do this. So it's time to do some practice problems with this. So the more practice you get with this, it's like doing the other mole conversions with compounds. The more practice, the better you're going to get at it. So just keep kind of plugging away at doing these.